Nearly all the molecules in your retina, which right now are absorbing light from the screen and transmitting signals to your brain. Nearly all the atoms in the cilia of your cochlea, which are gradually waving back and forth in response to the pressure waves produced by my voice. And even the molecules in your skin, which can feel gently the chair pressing against them, are all made of atoms that you have eaten, drunk, or inhaled over the past few decades. At the molecular and atomic level, it's replacement parts in almost all parts of your body. You are, quite literally, what you eat. As a consequence, your atomic composition reflects with great precision the mix of isotopes in the soil in which the vegetables and the grains you eat were grown, in which the grass on which your milk cow or your proto-lamb chop fed. Now, I'm a cook. In fact, it turns out that while I stand here pretending to be an astrophysicist, all the astrophysicists who have eaten my food agree that I'm a better cook than an astrophysicist, which I admit is an ambiguous compliment. I came about this through a slightly unusual route. My mother was British, which is usually not a good start, but my father grew every vegetable I ate when I was a child until I went to college, and so I learned to develop a tremendous respect for fresh food. Tonight, the meal I may make may consist of Tasmanian sea trout, accompanied by a sauce made from a reduction of shallots and Mexican tomatoes, perhaps some California salad greens, and a Chilean Sauvignon Blanc. So isotopically speaking, I'm a total mess. Less than 1,000 years ago, however, virtually all the food one ate was locally produced and consumed. And 10,000 years ago, hunter-gatherers and early agriculturalists certainly ate 100% locally. Now, it's true, of course, that some of the creatures they captured, birds, which can migrate long distances, and fish, which can swim a long way, might have added some variety to the isotopic composition of their bodies. However, migratory birds aren't very tasty because they have very strong muscles and very little fat, and in early days at least, primitive peoples weren't out fishing the center of the Pacific Ocean looking for migratory fish like tuna. They were more likely catching fish in local rivers. And so all of the atoms that were incorporated into the food chain, from the base plants that are the basis of all the food chain, all the way up to the carnivores, were local. And as a consequence, one can detect the signature of these local isotopic ratios in the bones left behind from ancient peoples. Several recent isotopic analyses of bones and food demonstrate the power of the atomic approach to human prehistory. Now, reconstructing the origins and travels of prehistoric, pre-literate people might seem best left to fiction writers, but in fact, isotopic analysis on the remains of Ötzi, for example, the Iceman, provide a detailed chronicle of his life. Ötzi was discovered by two alpine hikers in 1991 on the border between Italy and Austria. His body was half buried in a glacier and was extremely well preserved. Standard archaeological techniques revealed many aspects of Ötzi's life and death, but the isotopic analysis led to some real interesting breakthroughs. His stomach contents revealed that his last two meals were of chamois, the antelope in mountainous Europe from which that nice soft cloth derives, and red deer, accompanied by at least some primitive form of bread. His axe was almost pure copper, 99.7% copper, indicating a remarkable degree of refinement in the smelting of copper in Copper Age Europe about 5,300 years ago. An analysis of his clothing and other paraphernalia provided many details of life in the Copper Age of Europe. Atomic analysis of Ötzi's bone and hair, however, provided remarkable details concerning his personal history. Tooth enamel is fixed when the tooth is formed, so its isotopic composition reflects the diet of one's youth. And unlike most aspects of the body, not a lot of replacement parts are incorporated into the base of the tooth. Whereas one's bones remineralize or reincorporate new atoms as one eats and excretes over one's lifetime on a cycle that lasts from 10 to 20 years. And so the isotopic ratios in one's bones tend to reflect one's diet during adulthood. In looking at the oxygen content of Ötzi's bone and teeth, for example, we have a clue as to both where he was born and where he subsequently lived. Heavy oxygen, oxygen 18, precipitates out preferentially in rainfall because oxygen 18, H2O18, is heavier than H2O16, the normal isotope of oxygen. And so the water is evaporated from the sea and then moves over the land and gradually precipitates out, with the oxygen 18 raining out first, and the oxygen 16 being more prevalent at high altitudes farther from the ocean. Ötzi's teeth, it turned out, had a higher ratio of oxygen 18, indicating that in his youth he spent more of his time in the lower valleys to the south of where he was formed, whereas his thigh bone had sort of intermediate values of oxygen 18 to oxygen 16, indicating that later in life he lived at higher altitudes. Furthermore, radioactive isotopes of strontium and lead vary depending on the rock and soil type from which the vegetables and grains one eats is grown. And in this area of northern Italy, southern Austria, there are 4 distinct geological zones with rocks that erupted at various distinct times, yielding different strontium to lead ratios. The strontium to lead ratios in his teeth were found to match most closely the Isaac Valley, northeast of present-day Bolzano in Italy, suggesting that's where he spent his childhood. However, a dozen flecks of mica, presumably originating in the grindstone from which his bread flour was ground, could be dated using radioactive argon isotopes, the ratio of argon-40 to argon-39. Now, argon-40, argon itself, is a noble gas, and is produced from potassium-40, the decay of a naturally occurring radioactive isotope. Originally, dating was done by taking the ratio of potassium-40 to argon-40. The more potassium that had decayed, the lower the ratio, and that gave an indication of the age. However, that assumes that the rock began with no argon-40 present, and that's an assumption which is not necessarily fair to make. A refinement of this technique has been developed over the last couple of decades, in which potassium-39, which is always found in the mineral exactly in the same place as potassium-40, because of course the atomic structure of the 2 potassium isotopes are identical, and therefore they collect in the mineral in exactly the same place. Potassium-39 is irradiated with a reactor, with neutrons from a reactor, which reduces the radioactive decay to argon-39 with a half-life of 269 years. And so one has argon-39 trapped in the same places that the argon-40 from the natural radioactive decay occurred. What happens then is one heats the crystal very slowly, driving out the volatile argon gas. If all of the argon-40 that was present came from potassium-40, the 2 isotopes of argon leave the mineral at exactly the same rate. But if there's a variation, one can tell there was some argon-40 originally in the rock and can correct the dating technique. The age of the argon-39 to argon-40 dating of the mica chips suggests that they were about 100 million years old, consistent with rocks from the Vischgau Mountains, which are about 50 kilometers to the west of the birthplace of Ötzi, suggesting that after being born in the lower valleys, he moved higher up and spent his adulthood about 50 kilometers to the north. Ötzi's hair contained excess amounts of copper and arsenic, 2 non-organic minerals, suggesting that, to some archaeologists at least, he played an active role in copper smelting, and the axe he was carrying suggests that he had a close relationship with those who made tools out of copper in Copper Age Europe. Thus, Ötzi's diet, his travels, and his profession are all yielded up by the atomic analysis of his remains. Another example of using isotope ratios to unravel the history of a preliterate people comes from the Anasazi of the southwestern United States. Anasazi means the ancient ones in the current dialect of the Native Americans of the Southwest, and they had a civilization which thrived between the 5th and the 12th centuries and then abruptly vanished. We'll revisit this interesting historical period when we talk about the history of the Earth's climate, because from another set of dating techniques, we think understand what led to the collapse of their civilization. But over this several hundred-year period, they built major cities in northern New Mexico and Arizona, the largest of which is at Chaco Canyon, where the remains of a 800-room apartment complex, 4 stories high, and a whole complex of surrounding nearby villages suggests a peak population for the area of between 5 and 10,000 people, a major city for that period of time. More impressively, a major city for that very dry and desolate region of the country. The land surrounding Chaco Canyon is most unlikely to be able to support this huge population, so resources had to be imported elsewhere for food. Recently, analysis of corn cobs recovered from refuse pits in this area confirm a very far-flung agricultural enterprise for these Anasazi people. Calcium, number 20 in the periodic table, is an essential element for life, of course, and is found in some quantities in corn. Strontium, atomic number 38, lies directly under calcium in the periodic table, and therefore, as you recall from our discussion of the periodic table, has exactly the same electronic structure, and as a consequence, participates in chemical reactions in very much the same way. It, like calcium, has 2 electrons in its outer shell, which leads it to make a certain kinds of bonds. And therefore, it behaves very similarly to calcium in any chemical reaction that occurs, including the one that incorporates calcium from one's diet into one's bones. There are several different isotopes of strontium that occur naturally in the environment, including strontium 84, 86, 87, and 88. Now, strontium 84, 86, and 88 are all stable. They don't undergo any radioactive change, and they don't derive from a radioactive change. They are produced like the other elements we'll find in the cores of stars. Strontium 84 makes up only about 6/10 of naturally occurring strontium. Strontium 86 makes up about 10%, and strontium 88 makes up about 82% of all strontium available. It is not a surprise to find that strontium 88, an even-numbered isotope divisible by 4, is the most stable form of strontium and therefore makes up most of the strontium that we find in the natural world. As we'll learn when we study the creation of the elements in stars, isotopes that have numbers of nucleons divisible by 4, therefore can be composed of 2 + 2 neutrons and protons, or helium nuclei, alpha particles, and these tend to be the most stable and therefore the most common isotopes. So that's 84, 86, and 88. Strontium 87, however, while not radioactive itself, is radiogenic. That is, strontium 87 derives from a radioactive isotope, rubidium 87. Rubidium 87 has an enormous half-life, 47 billion years, 3.5 times the age of the universe. And so there's plenty of it around, and there will be plenty of it around into the future to decay into strontium 87. In a typical sample, strontium 87 makes up about 7% of all the isotopes of strontium present in a mineral. In fact, the ratio of strontium 87 to strontium 86 ranges from about 0.700 to about 0.750. And that ratio provides a key clue both to the age of the rock in which it is found and to the original composition of that rock, how much rubidium was present. Thus, over the surface of the Earth, we find hundreds of different regions with slightly different strontium to 87 to strontium 86 ratios, indicating different ages for the time that the rocks were extruded from the mantle of the Earth, and also different initial compositions from that location in the continental crust. Now, getting back to the Anasazi, the strontium isotope ratios from the Chaco Canyon corncobs did not match the strontium isotope ratios of the local soil, confirming the notion that the region was too dry and infertile to support a large population. In fact, it matched rather well the soil at the foot of the Chusca Mountains that are about 50 miles to the west, and the soil around the San Juan River floodplain about 56 miles to the north. 50 miles may not sound like much nowadays, but it was an enormous distance if that's where the bulk of the agricultural production of the Anasazi people came to feed the huge population at Chaco Canyon. Because recall, these people thrived between the 5th and 12th centuries AD. There were no horses or other pack animals in North America at that time. While the horse actually originally evolved in North America, following the demise of the dinosaurs 64 million years ago, the subject of one of our future lectures, horses died out in North America about 12,000 years before the present, about the same time that many of the other very large mammals of North America also met their demise. Fortunately, Horses did the reverse of humans about that time and migrated across the land bridge over the Bering Strait between Alaska and Siberia when the sea levels were much lower as a consequence of the Ice Age. Horses thus populated Asia and eventually Europe from North America, but by 12,000 years ago, there were no horses left in North America. They were only reintroduced at the time of Columbus's second voyage to the New World at the end of the 15th century, and then transported to Mexico and South America by the conquistadors and eventually repopulated North America. So throughout the time, the Anasazi were building this civilization around Chaco Canyon and developing a vast agricultural productivity in mountains 50 miles away. There was no way to transport all of that food to feed the 10,000 inhabitants of Chaco Canyon other than carrying it on human backs. Indeed, from the air today, one can see the elaborate system of trails, some over very steep cliffs, that led from the agricultural fields of the Anasazi to their capital in Chaco Canyon. My formative years corresponded to the peak of nuclear weapons testing in the atmosphere, and I carry the evidence of that human-induced set of isotopes in my body today. Of the large number of radioactive isotopes produced in the atmosphere by nuclear explosions, two are most biologically relevant. Strontium-90, notice that's not one of the 5 strontium naturally occurring isotopes, and cesium-137. As I've said, strontium is a chemical substitute for calcium and so often ends up in the bones. And cesium is a similar chemical homologue for potassium because it lies under it in the periodic table in the first column, number 55. Both isotopes have half-lives of roughly 30 years, which is much what makes them relevant to human beings. Isotopes incorporated into your bones at the time of youth decay with a half-life of 30 years, so over the first 30 years, half of them decay. Over the next 30 years, another quarter of them decay. Children, since they are rapidly absorbing calcium and therefore inadvertently strontium into their bones, suck up about 60% of the strontium that's ingested, whereas later in life, since for adults remineralization of the bone takes place much more slowly, only absorb about 30% of the strontium they ingest. The strontium-90 from weapons tests today produces about 1 radioactive decay every 5 minutes for every gram of soil. It's a pretty low dose. But it is a dose, of course, that's sitting in your bone right next to your marrow, and so when one of these pops off and the little particles go zipping out, they have a good opportunity to damage cells of the bone marrow. The atmospheric nuclear tests of the 1950s and 1960s have produced exposures of up to 10 rads, a unit we'll discuss in a minute, distributed very unevenly over the face of the United States, as indicated in this map. The natural background over this interval is actually comparable to that value, so this is a non-trivial addition to the amount of radioactive radiation that one is exposed to. The other significant radioactive isotope produced in bombs and in nuclear reactors are iodine-129 and iodine-131. These two radioactive isotopes have radically different half-lives, 15.7 million years and 8 days, respectively. This nicely illustrates the radically different decay rates that isotopes with different half-lives produce. In this diagram, you can see how the half-life of 8 days decays away very rapidly, where the isotope with the half-life of millions of years has a very steady decay rate over anything approaching a human lifetime. 1 week after an event like Chernobyl or the explosion of a nuclear weapon in the atmosphere, 1 gram of iodine-131 produces about 3,300 trillion decays every second, whereas 2 years later, this rate has dropped to 0, because the number of half-lives have gone by meant that all of the radioactive isotopes have decayed. For iodine-129, however, with this much longer half-life, the rates are about 10 million decays per second per gram, both for 1 week after the event and for 2 years after the event, and for that matter, for 2,000 years after the event, because the half-life is so much longer. Since iodine concentrates in the thyroid, the fallout from Chernobyl from iodine-131 has been linked to a rise in thyroid cancers among children exposed in 1986, the time of that terrible event, although the extent of the cancer epidemic is highly controversial. Equally controversial is the impact of childhood exposure from these nuclear weapons tests in the atmosphere on thyroid cancer rates amongst today's adults. If you Google thyroid cancer and weapons tests, you'll find almost any number you want, meaning there is still great controversy over this. The first nuclear explosion in the atmosphere, of course, was in August of 1945, when we dropped a bomb on Hiroshima and a few days later on Nagasaki in Japan. But these bombs were what we called atomic bombs. Now that's a misnomer, because changing around atoms is a chemical reaction. That's what a normal bomb, or TNT, does. Atomic bombs really meant fission bombs, splitting the nuclei of atoms to release energy. And throughout the late 1940s, we were testing these awful weapons to assure our safety in a very unsafe world. However, in 1951, a new kind of weapon, a fusion bomb or a hydrogen bomb, was developed with vastly more power, thousands of times more power, and tens of thousands of times more ability to create radioactive isotopes. So prior to 1951, the amount of exposure from atomic bomb testing was extremely small. Between 1951 and 1963, however, when hydrogen bomb testing in the atmosphere, both at the nuclear test site in Nevada and at the atolls in the South Pacific, pumped an enormous number of radioactive isotopes of an enormous variety into the atmosphere, and that signature remains both in the atmosphere today and in the bodies of those of us growing up at that time. The National Cancer Institute actually has a website in which you can estimate, and I emphasize the word estimate because, as you'll see, it's not a very precise estimate, your exposure if you were born before 1963 test ban. Remember, the half-life of the important isotope was only 8 days, so even if you were born in 1964, none of this radioactive material was left. 1963 was the end of testing in the atmosphere, and the way it came about is rather interesting. President Kennedy became convinced of the danger of nuclear fallout, which hadn't even been recognized a decade earlier, because of a study at Washington University in St. Louis of baby teeth. A scientist at Washington University asked all the people in the St. Louis area to collect the baby teeth, those teeth put under the pillow so the tooth fairy could come and take them, and send them to his lab so he could assess them for the amount of strontium isotopes in them. You recall from Ötzi that strontium isotopes build up in the teeth and remain there in the baby teeth and if the amount of strontium in the air was increased dramatically, or in the grass that the cows ate, the milk you drank, then as a consequence, the strontium in the baby teeth would also be higher. And indeed, he found substantial changes in the amount of strontium, indicating directly that American citizens were absorbing radioactive material from the environment put there by nuclear weapons testing. And this was a major impetus for President Kennedy to negotiate with the Soviet Union and to ban the testing of weapons above ground. Underground tests, which continued up until relatively recently, produced very little or no input of radioactive isotopes into the general atmospheric environment. Anyway, at the National Cancer Institute test site, what one does is enter one's date of birth to the day. This may sound like a slight bit of overkill, but remember, with a half-life of only 8 days, if you were born a month or so after a large nuclear test, most of its radioactive isotopes would have decayed away. 4 half-lives having gone by means only 1/16 of the material would have been left. So one puts in one's date of birth to the day. One next enters the county in which one grew up, because it turns out wind and rainfall patterns leave a very patchy distribution of where the radioactive isotopes settle on the grass and are ingested into the food system. Finally, one has to enter the kind of milk, cow's milk or goat's milk, that one drank as a child, because it turns out that goat's milk concentrates the radioactive isotopes more effectively than cow milk does. And one has to remember, which I had a little trouble doing, how many glasses of milk one typically drank in a day. So for me, I entered December 7th, 1950. I grew up in Plymouth County, Massachusetts, on the southeast coast of Massachusetts, and I drank only cow milk. I certainly don't recall goat milk even being an option in my neighborhood at that time. Whether I drank 1 to 3 glasses a day or 4 to 6 glasses a day, which are 2 of the options you're given, I can't frankly remember, but I put in 1 to 3. This program then calculates your exposure at 7.8 rads, where the word rad stands for radiation absorbed dose. And it gives a 90% confidence range of 3.1 to 31 rads, a rather large range. One can also actually get the dose per test. That is, the dozens of individual nuclear tests, each of which had silly names made up by the military, which, if you add them up, disturbingly does not add up to the estimated total dose that you received, suggesting some uncertainty in all of these calculations. Now, what is this rad? The radiation absorbed dose is a crude measure of the amount of radiation you get. In fact, the damage radiation can do to human tissue depends on the kind of radiation it is, whether it's gamma rays or X-rays, or whether it's electrons or alpha particles, or most importantly, if it's neutrons, which given their neutrality can penetrate very deeply into the tissue. And so there's a factor called the RBE, or radiation biological efficiency, which turns a rad into a rem. All of this alphabet soup here is not particularly important. We can estimate what the backgrounds are that one is naturally exposed to and compare that to what one gets from the nuclear exposure. So typically one gets about 0.3 rads per year from the background of cosmic rays, about 0.005 rads from a round trip to California, which I just did on an airplane. Because one is above the atmosphere, more cosmic rays hit you and your radiation dose is higher, and about 0.007 rads from a chest X-ray. These all to be compared to the 7 rads of exposure I received from nuclear tests. So 7 from the tests. Cosmic rays, those high-energy particles which bombard the atmosphere and we saw create, among other things, carbon-14, yield a rate of about 0.2026 per year times my 58 years, has a total exposure of about 1.5 compared to the 7 from the nuclear tests. From soil and rocks, naturally radioactive substances occur at a rate of about 0.016 rads per year, or again, multiplying by my age, an exposure of about 1 in these units. That's if one lives on the coast of the US. It depends greatly on where you live. In the Rocky Mountains, the rate is about 5 times higher, and there are places in Iran where the soil is very rich in radioactive isotopes, and the exposure rate is 1,000 times that of a typical place on the continental crust of the Earth. The food and water one drinks and ingests also contains radioactive isotopes. Carbon is in everything, and carbon-14, we've seen, is radioactive. Potassium also has this radioactive isotope. Potassium in bananas gives you a significant fraction of the exposure which you have. Doesn't mean you should stop eating bananas, because potassium is an essential element for the body, but some of it that you ingest is radioactive. If you add that up, a typical diet gives you about 0.04 rads per year, or again, multiplying by my age, about 2.3 rads of exposure, about a third that the nuclear tests provided. Radon gas, a naturally occurring gas in the atmosphere, which is produced from radioactive decay in the rocks, also is a significant source of exposure and is actually greater the better insulated and sealed your house is from the outside. This can be about 0.2 rads per year, or a total of about 12 rads, exceeding that of the exposure from the radioactive tests. And then for me, an important factor is airline travel. You get only about 0.0005 rads per hour, but since I've just passed 2.5 million miles on my American Airlines frequent flyer program, that means I've spent more than 5,000 hours in the air, yielding a rate of about 3 rads over my lifetime. Medical exposure is also not trivial and adds about 10% for most people averaged over their lives, although it's worth noting that a full CT scan, something that's becoming popular today, I don't think for very good reasons, yields an exposure of about 4.5 rads, almost as much as the entire exposure I got over 13 years of radioactive testing in the atmosphere. So my dose was about 7 from natural sources and about 7 from the tests. In other words, my exposure over the 12 years of my youth was roughly doubled. One should note, to put this in context, that the least lethal dose is about 450 rads induced over a very short period of time. So we're nowhere near that number there. Whether this low exposure over a long period of time produces a particularly increased risk of cancer is still a controversial subject to ongoing studies. We focused here on the inorganic atoms, oxygen, strontium, cesium, iodine, arsenic, copper, that are incorporated into our bodies as we consume our food, drink our water, and breathe in the air around us, whether from natural or man-made causes. These atoms come along in molecules that we need for sustenance, i.e. the H2O, the O in water, is something essential to life. They come along as elements required for specific bodily functions like iodine in the thyroid gland, and as chemical homologs that masquerade as essential elements like the cesium and strontium, or as simple contaminants like, for example, arsenic, things our body don't need at all but do get absorbed in the atomic influx that we absorb every day. Again, the fact that each atom of an element is identical and has a unique signature revealed by its electron energy levels, by its nuclear energy levels, and by its particular combination of mass and charge allows unambiguous identification. The mix of isotopes represented in each element carries clues to the source of that element in the food chain, the soil in which it grew, the water it absorbed, and the contaminants to which it was exposed. History is written in these atoms. It is the organic, carbon-based molecules, however, that form the bulk of our sustenance, and the 3 isotopes of carbon also hold direct clues to our diet. Next time we will use these clues to trace the history of agriculture, which is reflected at the atomic level in our bones.